hopefully we'll have sometime during Chapter 5 to kind of look at a few of the things that are from the counting techniques, which is in section 4.7. Probably would be a good chapter to read is section pages 184 to 189. They will not show up on any test, but having an idea of where some of these formulas are going to come from, it kind of helps you have a better understanding when we talk about these counting techniques, if you've kind of looked at those. And it's looking at whether or not when you're counting, if you're wanting certain things to happen in a row, whether or not the order matters, whether it doesn't matter, how many chances, how many different ways that those can be counted, and how many different ways it could happen is what that's looking at. All right, section 5.1 then, kind of reviewing through where we've been first, and then going with a preview of where this chapter is taking us. This chapter is going to combine the methods of descriptive statistics that we talked about in Chapter 2 and 3, and those of probability that we just talked about in Chapter 4 to describe and analyze. So we're bringing the different pieces together that we've already done. So we're going to look at probability distributions. Probability distributions describe what will probably happen instead of what actually did happen. And they are often given in the format of a graph, table, or formula. So these probability distributions is one of the key things that we're going to be really focusing in this chapter. First, we have to understand the concept of a random variable and be able to distinguish between discrete and continuous random variables. In this chapter, we will focus on discrete probability distributions. First question, what's it mean to be discrete? Where there is jumps. Okay, discrete is where you do have those jumps. You're jumping from, there's either one person that had a dog, or two people that had a dog, or three people that had a dog. There's no part of a person that you can have. So it's not continuous data. It's jumping from one value to that next value. So again, this is kind of focusing, giving you a preview of where all this is going real quickly. So all this I don't expect you to understand in one quick way of doing this. In this chapter, we will construct probability distributions by presenting possible outcomes along with the relative frequencies we expect. So when we're rolling a dice, in chapters 2 and 3, what we did was we counted. For rolling a dice, you have the options of 1 through 6. We counted how many times did we roll a 1, how many rolls of 10, how many rolls of 2. We counted how many of each one of those we got. We found the mean and the standard deviation based off what we actually did in our experiment. And so we were able to find what the mean roll was 3.6, what the standard deviation was 1.7 for this experiment. So that's where we've been. Where we're going with, or what we've done in Chapter 4, is we found the probability of each thing happening. We know that the probability, if we're rolling a dice, the probability we'll roll a 1 is 1 out of 6 chances. Of rolling a 2 is 1 out of 6 chances. And so we had what we have as our expected values that we would get. Chapter 5 is going to take those things and blend them together. When we were calculating out the mean and the standard deviation, to find the mean, you would add up all the values and divide by how many there are. Well, we would multiply x times the frequency plus 2 times 10 plus 3 times 9, and we would add those all up and divide by how many different total frequencies we did. That found our mean. Well, what we're going to do now then in Chapter 5 is I know my expected probabilities. And so I'm going to find what the mean expected value would be. We'll take I'm jumping ahead. We're going to take the 1 times the 1/6 plus the 2 times the 1/6 and figure out and divide. Actually, we won't have to divide because this is a probability already. And that'll tell me what I have as my expected values. And so we can calculate out our mean and our standard deviation from what we expect to happen. And notice that this time it is the population mean and the population standard deviation versus the sample mean and the sample standard deviation. So you're kind of blending the two things together that we've done from the beginning with Chapters 2 and 3 to describe data, and what we looked at with Chapter 4 of what we can expect from probabilities. And this is finding that probability distribution that we're going to be looking at. So Chapter 3, one would conduct an actual experiment and find and observe the mean, standard deviation, variance, and so forth. And then you can construct a frequency table or histogram. Chapter 4 finds the probability of each possible outcome. And now in Chapter 5, we present the possible outcomes with the relative frequencies we expect. Questions on kind of where we're going? So let's focus on what it means to be a random variable first. So this section introduces the important concept of a probability distribution, which gives the probability for each value of a variable that is determined by chance. We distinguish between outcomes that are likely to occur by chance and outcomes that are unusual, in the sense that they are not likely to occur by chance. Definition of a random variable. It's a variable typically represented by x that has a single numerical value, determined by chance for each outcome of a procedure. So when we were talking about rolling a dice, we're talking about that random variable x being the chances that we're going to get, the probability that we would have a 1 would be that x is my random variable. Or if we're drawing cards, we're looking for x being maybe a queen or maybe the ace of hearts, where we're trying to find a specific thing and it has a specific probability that it is going to occur. Our probability distribution as a description that gives the probability for each value of the random variable, often expressed in the format of a graph, table, or formula. So, did I pass it already? There it is. This is what we're talking about with our probability distributions. The x's, my random variable was whether I rolled a 1, 2, 3, 4, 5, or 6. The probability that each of these happen, and now looking at that probability distribution is organizing that information in a table. Not always, when we talk about these, are things going to have the same probability each time. Because if I was talking about, I'm trying to think of some good examples. Probabilities that somebody is a smoker or a non-smoker, well, that could be my two variables, and obviously the probability is not going to stay equal both times. Or maybe it's that you're a male smoker or a female smoker or a male non-smoker or a female non-smoker. And so the probabilities for all four of those different random variables would be different values. So the examples I've been pulling so far have really kept those probabilities staying the same. Rolling a dice, it's all 1/6 of a chance. But that's not always the case when we're talking about these random variables. When we talk about a discrete random variable, either a finite number of values or a countable number of values are our possibilities. We're not working with things that can have fractions and decimals. So I'm not going to be looking at, if I was talking about the amount of water in my water bottle would be something that's continuous, I'm not going to be using that in this part. I might be looking at how many water bottles are going to be in a vending machine, but I'm not going to be looking at how much volume of water would be in that vending machine. That's moving into something different that we'll actually cover later on this semester. Our continuous random variables means there's infinitely many values, and those values can be associated with measurements on a continuous scale without gaps or interruptions. That's when we had the decimals and fractions. Right now, we are focusing only on our discrete random variables in this chapter. We'll worry about the continuous ones later. But when we're looking at those discrete random values, it's either you have 10 bottles of water in the vending machine, or you have 11, or you have 12, or you have 35, but you're not having fractions and decimals. They're not going to fit half a water bottle in the vending machine. And so you're having that discrete values. We're not working with things that have that continuous scale yet. So looking at our probability distributions, the same one we already looked at already. If you roll a die, then the data is discrete, since you will either roll a 1, 2, 3, 4, or 5, or 6. And so then this is our probability distribution, where we have our random variables of what our possible outcomes are. We have the probability for each of those outcomes. If we were to put this as a graph, the probability histogram is very similar to a relative frequency histogram, but the vertical scales shows probabilities instead. And so now this is looking at having our discrete values. And so this is looking at the probability histogram for the number of Mexican American jurors among 12. And so the probability that we had 0, 1, 2, 3, 4, 5, all the way up to 12 out of the 12 jurors were Mexican American. Looking at those probabilities. So as we can look at this, we can see the one that's the most frequent. The one that happens the most often is that we have 10 jurors out of the 12 are of Mexican American heritage. Probability that 2 out of the 12 are Mexican American is looking at 0 out of the 12. So obviously this is not Trenton, Missouri that we're looking at pulling our jurors from as you're doing this week. So it definitely tells you something about the area where we were looking at. Questions on what that means? This is also a good one to show that the probabilities don't stay consistent. The probability that 4 out of the 12 was, what is that, about 0.001? Probability that it was 9 out of the 12 was at about 0.23. And so each of those probabilities are different as you're doing it. The sum of the probabilities have to add up to be 1 because all possibilities are represented. Questions? Also notice this gives you the fact that this has kind of a normal distribution or almost normal distribution if we ignore the fact, well, I guess it is kind of skewed because it does keep going over here a little bit further, doesn't it? This one is really actually skewed now that I look at it better. Because we have skewed one that the tail's going, it's not very good. That's probably a better way of writing it. So our tail's heading off to the left. This one's a left skewed distribution. Oops. All right, if I want to find or describe my probability distributions, this one I already mentioned. All possibilities have to be represented, therefore the sum of all the probabilities has to be 1. You have to have 100% of the values to be looking at a probability distribution. If I was looking at the jurors and I left out, out of the 12, and I just left out the fact that there might be 12 out of 12, then they're not all going to have all possibilities represented. Therefore, I can't do anything with that data. I need to know what those last values need to be. So they have to add to be 1. Each individual probability has to be between 0 and 1. You can have the probability be 0. On that last one, they were trying to say that there was no chance that you're going to get 0 out of the 12 jurors being Mexican American, that you're going to have all of them that are not Mexican American. No chance of that happening in that jury, in that area. So you're going to have the probability be 0. You can have a probability be 1. 100% of the time, if you have a coin that's both sides are heads, the probability that you're going to flip a heads is 1 out of 1. 100% of the time you're going to get, or your probability is 1, not 1 out of 1, but probability is 1 because 100% of the time you're going to flip it and get a heads. No, you're not going to get it to land on its side. So as you're looking at these, each individual probability will be between 0 and 1, including those endpoints. The sum of your probabilities has to add up to be 1 if we're looking at a probability distribution. Did our dice example meet those requirements? Is the sum of all my probabilities 1? If I add 1/6 6 times, will I get 1? Is each of these probabilities between 0 and 1? Okay, so this is a good example of a probability distribution. Again, this is one where all my probabilities are equally likely. Let's look at a couple other examples from the book. If we look at page 214. First of all, looking at number 8, the caffeine nation. In the accompanying table, the random variable x represents the number of cups or cans of caffeinated beverages consumed by Americans each day. Is this one a good example of a probability distribution? So give me a thumbs up or a thumbs down on number 8. Everybody that's voting so far is giving me a big thumbs down. What's wrong with it? Okay, it doesn't equal 1. When we add up all the probabilities, what's it come to? 0.75. Well, what's wrong? Okay, what'd they leave out? Does everybody you know drink 3 or fewer cans of soda? What about those people that drink more than 3? We've ignored them. Not necessarily. Not healthy, I'll go with, but not necessarily obese just because of that. But we are definitely looking at, there is that possibility there's people that drink 4 or more. You can't ignore them and just leave them out of there because you don't like their lifestyle. You got to include it in there. And so that's accounting for the other 0.25. So according to this data, 25% of Americans drink 4 or more cups or cans of caffeinated beverages a day. Wow. Okay, so looking at that, so number 8 we're giving a thumbs down to, even though each one of those separate probabilities was between 0 and 1. How about number 10? Before you vote on number 10, let me explain what that last part says. On number 10, number 5 is saying that there's 0 plus. That means the probability, and I guess I should read the question. This is groups of 5 babies are randomly selected. In each group, the random variable x is the number of babies with green eyes. When we talk about the 0 plus, it's saying that probability is very, very, very close to 0, but it's not exactly 0. It's so close that when we do the calculations, we're going to round it to 0 because we're rounding probabilities to 3 decimal places. And rounded to 3 decimal places, it's 0. But it's not exactly. And so that's what that 0 plus is going to use. As we do calculations, we'll count it as 0. But it's a little bit more than that. So is this one thumbs up or thumbs down of whether or not that's a probability distribution? Okay, as you add them all up, do they add to be 1? Is each individual probability between 0 and 1, including those endpoints? So this would be a good example of a probability distribution. So this is telling me is the probability that if I take 5 random babies, the probability that out of those 5 babies that none of them have green eyes is 52.8% chance of that. The probability that out of those 5 babies that 4 out of the 5 have green eyes is a 0.001 as your probability. So a 0.1% chance that you're going to have 4 out of the 5 babies with green eyes. Questions on what that's saying? And the chance that 5 out of 5 have got green eyes is basically 0. Now, if I wanted to find, because we already said we're going to combine this probability distribution and use it to find my mean and my standard deviation and that kind of stuff. Well, how do I do it? If I want to find my mean, to find my mean, I'm going to take the sum of the x values times the probability that x occurs. So we're looking at having our random variables are numbers, and I guess that kind of does change from what I said earlier. When we were talking about the female smoker or the female non-smoker, that won't be in this part of things because those are categories, not numbers. So we can't do that here. If we're looking at this one, then we will have that x being your random values. So we're looking at having 0 green eyes, 1 green eye baby, 2 green-eyed babies, so forth, all the way up to a possibility of 5 out of 5 green-eyed babies, times the probability that that occurs. Multiply those first, and then add up that product. So pay attention to your order of operations because it matters. You have to take your random variable times the probability that it occurs, then add up all of those products. If I'm trying to find my variance, and notice these are for population mean, population variance, you're going to take the difference between your x value, your random variable, and your mean, square that value, times the probability it occurs, and add up each of those. If you know the variance, how do you get the standard deviation? How do I get sigma if I know sigma squared? Square root it. Now that's a shortcut for it. So if I know once I know the variance, I can take the square root of this. Now, this is the shortcut for doing this. If you're doing it by hand, this is looking at what's actually happening, because your variance is saying, well, how far away from the mean is it? And so you're finding how far away from the mean it is and the probability that that value happens. Shortcut is to take your values and square them times the probability, add those values up, and then subtract that from the mean. So that is a shortcut if you had to do it by hand, which would be a little bit faster way to do it when we're doing it by hand. But it's still telling me how far away, because variance is looking for how far away from the mean is my values. Standard deviation then is converting that back into the same units that we already had. And it's just telling me, it's giving me a good idea of how far away from the mean am I. Now, standard deviation is always positive. It's related to those z-scores, because z-scores were just really telling me how many standard deviations above or below the mean, and it had a direction. Your standard deviation is just telling me how far away from the mean is this value. I guess actually your z-scores is just a little bit more than that standard deviations. It's looking at what the average standard deviation it is away from it. Z-score is telling me how many standard deviations away it is, above or below. So let's look at number 10 on page 215. If I want to find my mean and my standard deviation of that same one that we've already said is a probability distribution, if I want to find my mean, I need to find x times the probability that x occurs and add all of those values together. So what I'm looking at doing to find my mean, and this is the population mean because it's coming from my probability distribution, I am going to take the 0 times the probability that it happens, which I could ignore, writing that down, the 1 times the probability that it happens, and go through and do this for each of those. So as you're doing that, what are you guys getting? Now, one thing we haven't talked about yet is how do I round this? When we're rounding things, when we were looking at that Super Bowl scores, I told you guys to round it to 1 decimal because your scores were all integers. If we look at what our values are, what are the values for x? The values are 0, 1, 2, 3, 4, 5. So you're going to round it to 1 more decimal than your random variables are. So if they're whole numbers, that means this one's going to round to 1 decimal. So my mean is 0.6. The mean number of babies with green eyes out of 5 babies is 6/10. So it's a little bit more. It's better than 0, but it's less than 1 that you're anticipating seeing of how many babies you're going to have out of those 5 babies with green eyes. Questions? Now, if I looked at finding my standard deviation, as I said, if I'm trying to find the standard deviation, first thing we need to do is find the variance, and then we'll take the square root of that. It's easier to do it this way, where I'm going to find the x's and square them times that probability, add all those up, and subtract it by the population mean squared. When we do put the mean in there, we'll put it back in as that being that 0.599 so we don't have any rounding errors. So don't use your rounded value, use the original value we had. So we'll find sigma squared first, and then we'll find the variance first. No. No. Yeah, those are important in this. It depends if you know what you're doing when you put it in next. Go ahead. Don't forget the 0. All right, so as you're doing this by hand, what are we coming up with? So getting 0.49 something, I think, or something close to that. Anything even remotely close, or is it 0.049? I don't remember what the number is. I didn't do it by hand. Did anybody get an answer? Well, I'm trying to do it in my head, so I could be wrong. What are you coming up with? Okay, that's probably right. Yeah, it is. 0.526 is good. Is that what you were getting, Shelby? Oh, okay. Yeah, I want the whole thing. Okay. So now, if we're getting that sigma squared, so our variance is 0.526, how do I find my standard deviation? Which we're going to round to 1 decimal of being 0.7. So this is telling me how far off we're anticipating those means. Questions there? So now the mean number of babies that we anticipate is 0.6 with a standard deviation of 0.7. And this is the mean number of babies with green eyes out of the 5 babies that are going to be randomly chosen. Now, round off rule, round results by carrying 1 more decimal place than the number of decimal places used for the random variable x. So since most of the time your random variable x will be a whole number because we're dealing with discrete data, then you're going to round it to 1 decimal place most of the time when you're doing this. But keep in mind that the data is the x value. The probability, which will be rounded to 3 decimals, is just a probability that x occurs. So you're rounding it compared to x, not compared to the probability. So if I want to use the calculator, which Aaron's already been trying to figure out how to make that happen. When you go to use the calculator, put list 1 is your x values, list 2 is the probability that x occurs. So go ahead and put those 2 things in. So put the x values in as list 1, put the list 2 as being the probability that x occurs into your calculators. And keep in mind to do that, you're going to your stat and then just edit. Clear out anything that's there. Yeah, do this for number 10. And do make sure you put 0 in for 5. So it does have to have something there. They do look different. Okay, now that we have that, you're doing the same thing we've done before. Go to your stat, arrow over to calculate, and we're doing the 1 variable statistics because I'm still trying to find my mean and my standard deviation. But the thing is, it's not just from list 1. It has to incorporate both list 1 and list 2 because list 2 is telling me the probability that occurs. So you have to do list 1, comma, list 2. So I went over from stat, to calculate, and I did number 1, which is my one variable statistics, to do list 1 and list 2. And then it's going to tell me my mean, which we already said was 0.6, which we already found was 0.599. That's telling me what that mean is. My population mean, or my population standard deviation, is the 0.725, which was the 0.7 that we already rounded to. If I absolutely had to have variance, I can take the 0.725 and square it, and it'll tell me what my variance was, which was that 0.526 we had earlier. Questions using a calculator to help you with that? Okay, figuring out what's usual and unusual then. Remember our range rule of thumb was the fact that 2 standard deviations is what's usual. So your usual values happen within 2 standard deviations of the mean. So in this case, my maximum that I would anticipate of seeing would be my mean plus 2 standard deviations, which in this case would be that 0.6 plus 2 of my standard deviations of 0.7. So that'd be 1.4, which would be 2 babies out of the 5 would be usual of seeing with green eyes. Taking my mean minus 2 of those standard deviations is going to give me a negative number, which obviously doesn't make sense. So in this case, we anticipate between 0 and 2 babies would be usual to see out of those 5 of having green eyes. Getting a sample that had 5 babies that had more than 2 that had green eyes would be unusual. Questions there? So that usual values is not changing what that's saying. It's still telling me it's within 2 standard deviations of my mean, above or below. Now, identifying what is unusual from our probabilities. The rare event rule for inferential statistics. If under a given assumption, such as the assumption that a coin is fair, the probability of a particular observed event, such as 992 heads in 1,000 tosses of a coin, is extremely small, we conclude that the assumption is probably not correct. If I'm flipping a coin and I get 992 out of the 1,000 flips is going to be a heads, I'm questioning whether or not that coin is rigged. It sounds like a weighted coin to me because the probability of that happening is extremely small. And so that's in that rare event rule. That would be something I would anticipate that the assumption that it was a fair coin would be a false assumption. So identifying what we think of as being unusual. When we're trying to figure out what we mean by unusual for this, well, we already said 95% of the values fall within 2 standard deviations of the mean. So if it's not usual, then it's the other 5% that's on those extremes. And so we use 5% as our range rule of thumb. Unusually high, X successes among N trials is an unusually high number of successes if the probability that X or more is less than or equal to 0.05. It's unusually low if X successes among N trials is an unusually low number of successes if the probability of X or fewer is less than or equal to 0.05. So determine if these are unusual. The probability that we have exactly 5 green-eyed babies, what was the probability that was 5? That was 0, or your 0 plus. So is that unusual? That is definitely smaller than 5%. So that's definitely unusual. What's the probability that it's 4 or more babies? What was the probability that's 4? Isn't that 0.01? 0.001? Is that unusual? Definitely less than 5%, so still unusual. And notice I'm just adding up the probabilities. What's the probability that it's 3 or more babies? What is the probability that it's 3? 0.013? Is that still less than 5? Still less than 5, so still unusual. So if I asked you what's the probability, or is it usual to see that I have 3 or more of those 5 babies with green eyes, it's still unusual. Now if I added in the 2, the probability that there was 2 is large enough that it's now brought me over the 5%. We'll do the expected value later. Oop, not too far. Homework. I think 28 is the only one I get to knock off. Nope, I get to knock off both 27 and 28. Oh, actually I'm 25. So you guys get to stop at 23. So we'll do the rest of those next time.